All right, we're looking this week at probability. Now, there's not going to be a lot of functions in R that we're going to be using, so this is more of a kind of an introduction to a lot of these concepts, which are going to be important to know as we go forward and apply statistics methods to some data. The reason probability is important is because well, a few things. One is that the science of statistics, usually we're basing it on the idea that we have, excuse me, a random sampling from a population. And that in itself means there's this sense of like the probability of this or that or that. So it's important to understand when you're taking a random sampling from a population, what kind of things can you expect? Also, this will prepare us to understand some ideas about probability distributions, which are models that we often use for populations. So anyway, let's go into some of the basic concepts of probability. So, people talk about the probability of something happening, talking about the chances that it will happen. What are the chances that the Red Sox will win, the chance of rain tomorrow. And so we kind of have this sort of very vague sense of what probability is or chance is that we deal with every day. We're going to formalize some terminology and concepts so that we can dispense with some of the vagueness around probability. So we're going to start with the idea of a random experiment, which is some sort of phenomenon or action or something that has an observable outcome, but it's an uncertain outcome. So it leads to one of several possible outcomes. When you flip a coin, there's two possible outcomes, but it's uncertain which outcome is going to occur. The probability of an outcome is the theoretical proportion of time that the outcome would occur if it was to be observed and repeated infinite number of times. So what proportion of times would we be getting ahead if we flip a coin an infinite number of times? The theoretical proportion is 50%. And I know that some people say, well, what if you are good at flipping? What if this and that? Yeah, we know. And incidentally, a lot of people, a lot of examples are, there's the example of an unfair coin is sometimes given. It turns out that actually flipping a coin is always pretty much 50%. But if you twist or spin a coin, it actually, the heavier side of the coin does make a difference. There was some research that was done that showed that, in fact, the side of the coin that is, if you flip a coin, just let it land, the side that is facing up when you start the flip has a very slightly higher chance of being face up when it lands. And it's a little bit technical, the reason why, but it doesn't have to do with wind or anything like that. So when we have a random experiment, some observable phenomenon with an uncertain outcome, these outcomes are just like, what are the possible things that can happen? And they need to be like distinctly observable from each other, for example. So one outcome an outcome could be the sum of the two dice that are rolled. So what is the total of the two dice? That would be the outcome of the experiment of rolling two dice, or whether a person responds well or doesn't to some therapy, the volume of eggs in a clutch laid by frog. So every time that a clutch of eggs are laid, it's uncertain how much it's going to weigh. So that's an observable outcome. An event is, in technical terms, it's a subset of the outcomes. But we would call it like some of a collection of the outcomes make a quote unquote event. And so the sum of rolling two dice being 7, there's not just one outcome that could result in a 7. So all of the different outcomes that of rolling 2 dice that result in a 7 are the event of rolling a 7. For if 22 out of 30 patients had a good response, so it's a little unclear actually. How that would be the event, I would say. But the total volume, say, oh yeah, so I see what it's saying. It's if the event being 22 out of 30 having a good response, 22 having a good response, it could be any 22 of them, right? So it doesn't mean the first 22 have a good response and the remaining 8 don't. So there's many ways in which out of 30 people, 22 of them could have good response. For the eggs, the total volume larger than 750 cubic millimeters. Yeah, I mean, it could be 751, 752. Any volume greater than 750 would be an outcome in that event. So sometimes we write events using this like bracket notation as a way of showing that these are events that are in a set together. The event of rolling a number smaller than 3 would be the event of getting that contains outcomes 1 and 2. Those are the only 2 outcomes, which would mean you'd say, oh, I rolled less than 3. So we would say that 2 events are disjoint or mutually exclusive if they can't both occur at the same time. That's what mutually exclusive means. I think that's the more common term, is mutually exclusive. We would say the term disjoint has to do with set terminology. Excuse me. So in this case, looking at if one event is we roll a number that's less than 3, that would be a 1 and a 2. The other event would be rolling a number that's greater than 1 and less than 4. So that would be the 2 or 3 would be in that event. Those 2 events are not mutually exclusive, because if you roll a 2, both of those events have occurred. But if there was another event rolling a 4 or a 6, that event is mutually exclusive with either of those 2 other events, because you can't roll a number that's lower than 3 and an even number greater than 3 at the same time, right? That's mutually exclusive. Now, if 2 events are mutually exclusive, if they're disjoint events, then the probability that either one or possibly both occur is written like this. So we use this notation where we have this U symbol. It looks like a U, but it's like a cup. Well, that's the techie term. We call this the probability of A union B, meaning if either event A occurs or event B occurs, or if both of them occur, then the union of the 2 events has occurred. Like, right, that we just need either one or the other, or possibly both. Now, if they're disjoint, of course, they can't both occur. So we don't to find the probability that one or another disjoint events occur, you just add up their probabilities. There's no overlap to worry about. So the probability of so if you look at the previous slide, right, the probability of event A is 2 out of 6. Because there are 2 ways in which this outcome can occur, and they're equally likely, right? 2 out of 6. There's 2, and for event B, it's 2 out of 6. And because they're mutually exclusive, the probability that A or B occurs would be 2/6 plus 2/6, which is 4/6. And this is true if you're looking at more than 2 disjoint events. You just add up their probabilities to find out the probability that any one of them occur. Now, if 2 events are not mutually exclusive, that means there's some sort of an overlap. Here we're looking at the probability of drawing a diamond or a face card from a deck of 52 cards. So you can see that there are 13 diamonds in the deck, and there are 12 face cards in the deck. So there is a probability of 13 over 52 that you draw a diamond, and a probability of 12 over 52 that you draw a face card. But the probability that you draw a diamond or a face card is not just the sum of those two probabilities, because if you did, you have to realize you're counting the jack, queen, and king of diamonds twice, right? So how do we correct for that? We're going to subtract the probability in the middle so that it's not counted twice. So the probability of a union of two events is going to be the probability of the first plus the probability of the second minus the probability of the third. And we use this downward facing symbol to mean the intersection of two events, meaning both events occur. In this case, a diamond face card would be the intersection of event A and B. So we have a union and we have an intersection. A union means either or, and an intersection means both, or and. Now, if we take all of the possible outcomes, every single possible outcome, and collect them all together, we call that the sample space. And so if we have like outcomes 1, 2, 3, 4, all the way up to some number k, then the sample space can be written as just this is set notation that we have here, this like bracketed list, O1, O2, all the way up to OK. That's just a way of writing this set, the collection of all of these outcomes. And so, for example, for the die tossing experiment, you can get a 1 through a 6. So the sample space would be those numbers 1 through 6. That's the possible outcomes, the list of all possible outcomes. So so one fact about this is, because we've exhausted all possible outcomes in this list, if we add up all of their probabilities, all of the outcome probabilities, and the outcomes are mutually exclusive of each other because they're just outcomes. They're like elemental. There's no overlap. It's the events that might overlap, but the outcomes themselves are just like, yeah. If we add up all of the probabilities of the outcomes, it'll add up to 1. If we've made an exhaustive list of every possible outcome, exactly one of those outcomes must occur. So the probability that one of them occurs is 1. It's 100% sure. It's certain. Once you understand what the sample space is, you can look at the complement of an event, which is all of the outcomes that are not part of that event. So in this case, if event D was rolling a 2 or a 3, the complement would be not rolling a 2 or 3. And so that would be rolling a 1, a 4, a 5, or a 6. So that's a complement. Just so an event and its complement together make up the whole sample space. We use, sometimes we'll use this notation, which is the little superscript letter C to represent the complement. I've seen also a little apostrophe used, and I've also seen a line on top of the letter A, all of them meaning a complement. This text uses the letter C for the complement of the event. So A with a superscript C would be the complement of event A. Now, two events are independent, and this is important that you have this concept distinct from mutually exclusive. Two events are independent if the probability that both occur is just the same as the product of their two probabilities. Another way of thinking of independent events would be whether or not one event occurs has no influence on whether or not the other event will occur. Okay, so whether or not event A occurs, if in this situation, let's say I'm interested in the probability. Let's say the probability that I roll a 1 on a blue die and a 1 on the green die. The two dice are independent of each other. So you can think of it like there's 36 possibilities, and the probability of getting a 1 and a 1 is going to be 1/6 times 1/6, 1 out of 36. And you can see that in this chart. Only one square out of the 36 squares represents getting 2 1s. So those would be independent events. Independent events are not mutually exclusive. In fact, if two events are mutually exclusive, meaning if one event occurs, it prevents the other event from occurring, that means they're definitely not independent, because whether or not one event occurs has a huge influence on whether the other event occurs, right? So mutually exclusive events can't both happen at the same time. Independent events can definitely happen at the same time. All right, now that we have the idea of independent events, let's look at this idea of conditional probability, which is, let's look at this. So what we have here is a proportion of deaths in different age groups for small children. And so for those children who did die during these ages, what we have here are a bunch of different causes, all right? And you can see during the first 12 hours, death due to immaturity, that's the bottom bar, is about, I'm going to estimate, about 67% of deaths. So if a child dies during the first 12 hours of life, there's a 67% chance that the death was due to immaturity. If you look at from 12 to 72 hours, if a child dies during that period of time, the chances that it's due to immaturity is roughly about 15%. So you can see that it's not the same proportion. What we have then is we can kind of look at, one question is to say, if a child dies, what's the probability it's due to immaturity? That question doesn't condition it on the age. But if I say, if a child dies within the first 12 hours, what is the probability it's due to immaturity? I've conditioned this question on the age being less than 12 hours, right? That's a conditional probability. So let's define that a little more formally. Or maybe let's think of this as another kind of example of why a conditional probability is not the same as probability. If you might think, like, ask yourself, what's the probability a randomly selected individual in the population is taller than 6 foot 4 inches? And this probability might come out to be, it might be something like, maybe it's like a 1 or 0.5%, right, of the US population. But if you know the person is a professional basketball player, if you know they're a professional basketball player, now does that change the probability that this individual is taller than 6 foot 4, right? Is the proportion of basketball players that are above 6'4" the same as the proportion in the total population? Obviously not, right? So if we condition this probability question, the probability that somebody is taller than 6'4", condition it on some known information about them, given that they're a basketball player, for example, it changes our probability estimate. That's a conditional probability. So the conditional probability of an event A, given that some other event B has occurred, is the probability of A knowing that B has happened, right? And we denote it with this vertical line. So this is read as the probability of A given B. And so here's an example. If we were to toss a coin 3 times, right, you can get heads or tails each time. 50-50 chance, so which is to say 50% chance of heads. Let A be the event that exactly 2 heads. You get 2 heads. And B is the event that at least 2 heads, all right? So A would be you get 2 heads. Either it's on the first and the second, the first and the third, or the second and third. B is the event that at least 2 heads have occurred. So it could be all 3 of them were heads. So what's the probability? The probability of A given B is that if we know that at least 2 heads have occurred, what's the probability that it was exactly 2 heads, right? We can think of all of the possible outcomes that are in event B, which is you could get head, 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 you get head, head, tail, head, tail, head, or tail, head, head. Those are the 4 outcomes. And of those 4 outcomes, 3 of those outcomes are in event A, right? So the probability of A given B would be 3 out of 4. Essentially what we're doing when we take a conditional probability is we're shrinking down our sample space to be the given event. That becomes our new sample space, and we calculate our probability based on that as the sample space. So here's a formula to calculate a conditional probability. As long as the event is possible, the probability of B isn't 0, then the probability of A given B is the probability that both events occur divided by the probability of B. In this case, the probability of at least 2 heads divided by, the probability of at least 2 heads and exactly 2 heads, which is actually the same as exactly 2 heads. The only way that you can have at least 2 heads and exactly 2 heads is if you have exactly 2 heads, right? So the probability of exactly 2 heads divided by the probability of at least 2 heads, it's 3/8 over 4/8. Work out the math and it comes out to 3/4. Now, if the probability of A given B is equal to the probability of A, that means that A and B are independent. It's kind of like saying, if you know whether or not you know event B occurs, if you knew it occurs or if you had no idea, if it doesn't change your probability calculation for event A, then that means that they're independent. Knowing B happens gives you no information about event A occurring. Now, the conditional probability formula allows us to calculate the probability of A and B occurring even if they're not independent of each other. If you flip the formula around, it has to do with basically you just multiply both sides of this equation by probability of B, and you get this. The probability of A and B occurring is the probability of A given B times the probability of B. So this is going to be true for all the time. And if it turns out that the events are independent, the probability of A given B is just the probability of A, as we said in the previous slide. So this simplifies to be the multiplication rule that we have for independent events. Anyway, that's why we call this the general multiplication rule. This is how you calculate the probability that events A and B occur, even if they're not independent. It works if they're independent, it works if they're not independent. So we're going to look at a kind of a consequence of the conditional probability formula, which is known as Bayes' theorem. And a great example of Bayes' theorem is this kind of counterintuitive example. It's the predictive power of a diagnostic test that isn't always accurate. All right, if you get false positives or false negatives, how you can calculate the likelihood of some a disease, for example, being actually present. So here are some examples of some chromosome. If there's an additional chromosome copy being attached to another chromosome during reproduction, so there's trisomy 21 is Down syndrome, which occurs in about 1 out of 800 births. The trisomy 13 is that's going to occur about 1 out of 16,000, and then trisomy 18 is about 1 in 6,000. Unless you do a genetic test, which you can do nowadays, before that there was a blood test that people would do. They would look for certain markers, and the test was not always accurate, and that's what we want to look at the probability of. the mathematics around. Okay, let's see. So this just gives some of the context around how this works, right? So the CFDNA consists of copies of the embryo DNA present in maternal blood. This advances in sequencing DNA provide the possibility of a non-invasive testing for these disorders using a blood sample. So the initial testing of the technology is done using archived samples of genetic material from children whose trisomy status was known. So the results are not, it's not 100% certain, but it's pretty good. So what we have are two kind of measures of this test: the sensitivity of the test and the specificity of the test. So out of the 1,000 unborn children with one of the disorders, about 980 have tested positive. So if the condition is present, then you can see 980 out of 1,000 times the test came back as a positive result. Out of 1,000 tested that did not have the disorder, it came back as a negative 995 out of 1,000. So you can see there are a handful of cases out of this sample, out of the 1,000 who had the disorder and 1,000 who didn't. There's a handful where the test came back incorrect. Let's look at the probability. These are conditional probabilities. So the designer of in a diagnostic test, you want it to be very accurate, which means you want it to have high sensitivity and high specificity. You want it to give very few false positives and very few false negatives. So here's an example. A family with an unborn child is undergoing testing. They want to know if the likelihood of the condition being present if the test is positive. Suppose the child has tested positive for trisomy 21. Okay, what is the probability that the child does have trisomy 21 given a positive test result? You might think, oh, well, because it has such high sensitivity, it's going to be like 98%. If you go back, right, if the child had it, 980 out of 1,000 tested positive. So you might think a positive test result means you have like a 98% chance. That does not turn out to be the case. The key thing is to realize that these conditions occur in a very small number of children in the population to begin with. Let's see how the math works out. Okay, we're going to create some notation. All right, so we're going to say D represents the event that the disease is present, and so its complement is that the disease is absent. The T with the positive, we're going to use that notation for a positive test result, and T with a negative as a negative test result. This is just the notation that we're choosing. We could use other notation, but this is what we're using. You could use complement instead of plus and minus, but it makes a little bit more sense to use plus and minus. It's just notation. So this is some of the terminology expressed as conditional probabilities. The sensitivity of the test is the probability of a positive test result given the disease, and the specificity is the probability of the negative test result given the absence of the disease. That's how we read these formulas. Now, a false negative rate would be the probability of a negative test result given the disease is present, right? It's 1 minus the sensitivity. And the false positive rate is the probability of a positive test given the absence of the disease. And it's also 1 minus the specificity. Here we have the sensitivity and the specificity, so we know some of these numbers. Okay, a couple other little things before we get into the math. Sorry, I keep teasing you with this, but we're going to get into the math in a moment. If a person tests positive for the disease, the positive predictive value of the test is the probability that the person has the disease, given that he or she has tested positive. So here, it's the probability of the disease being present given the positive test result. This is not the same as the sensitivity. The sensitivity is the probability of a positive test result given the disease being present. It's not the same thing. Probability of T positive given D is the sensitivity, but the math is different. Okay. Now, Bayes' theorem is essentially, it just builds on the conditional probability formula. The probability of A given B can be calculated from the probability of B given A and the probabilities of A and B separately. So here, and the probability of it, I don't want to get too much into the formula, but like where it comes from and everything, but basically it comes from just playing with the different ways of expressing conditional and probability of intersections. So Bayes' theorem usually is expressed in a more complicated form, where the denominator is actually split up, because the probability of B occurring can be written as the probability of B and A plus the probability of B and not A. You kind of split up the event B over different cases of A. And then we kind of split up the probability of, we rewrite the probability of B and A as using the conditional probability formula. So then what you get is this kind of long formula that's very hard to memorize. But the key thing here is that it's all in it can be written all in terms of the sensitivity and the specificity of the test. Okay, so we're going to take this formula and we're going to calculate. We're going to put it in terms of T positive and D and all that stuff. All right, so the probability that the disease is present given the test result is positive is the probability of the disease and the test result being positive divided by the probability of the test being positive. Now, what's the probability of the test is positive? It's the sum of two probabilities. The probability that the disease is present and the test is positive, plus the probability that the disease is absent and the test is positive. Now, those two can be rewritten using the conditional probability formula, the general multiplication rule. That's the probability of T, the test is positive given the disease, times the probability of the disease is present, plus the probability that the disease, that the test is positive given absence, times the probability it's absent. So this is what it is. It's the sensitivity times prevalence over sensitivity times prevalence plus 1 minus the specificity times 1 minus prevalence. Now we can plug some numbers in. We'll see. So for trisomy 21, the prevalence is 1 out of 800 births. That was given. And we had the sensitivity. The sensitivity came out to be 980 out of 1,000. So the specificity is 995 out of 1,000 births or tests, right? Like that's how many of those children did not have the disease and they came out back as a negative test result. Now what I'm going to do is so I'll write these as 0.98 for the sensitivity and 0.995 for the specificity. So the probability that the disease is present given a positive test result is going to be 0.98, the sensitivity, times 1 over 800 divided by 0.98 times 1 out of 800 plus 1 minus the specificity, which is going to be 0.005, right, times 1 minus the prevalence, which is going to be 799 out of 800. So this comes out to rounded off about 0.197, so 19.7% chance. So even though they got a positive test result, that doesn't mean there's a 98% chance that that trisomy 21 is actually present in the unborn child. What it means is there's a 19.7% chance. And the key thing to remember is it's because it's possible that this is a negative, that's a false positive. So what we kind of looking at, what's the proportion of true positives out of all possible positives? The true positives and the false positives. And that depends on how rare the condition is in the population. So the prevalence has a big influence on this predictive power. All right, so those are some of these concepts that we'll see this week and we'll work with in the lab. Hope this isn't too mathy, but I'm sure we'll get through this stuff together. All right, bye.